Hello everyone. I'm going to do some revision slides for AQA assembly language and the processor instructions for AQA A-level paper 2. Okay, computer science. So the processor and its components, it has these components here: arithmetic logic unit, which does all the arithmetic and logical operations. Fixed point and floating point arithmetic, logical operations, and or XOR, and shift operations. So we're going to look at some of those instructions. The control unit is the main function, which brings the instructions from memory to decode them and successfully execute them. So we're going to have a look at the fetch, decode, execute cycle as well. The clock is like the conductor to all of this. So like somebody beating a drum on a ship, telling everybody when to row, the clock likewise sends out a pulse so that all these components of the computer processor work together. And then we have a register, which is a bit like the calculator, a bit like the display on your calculator, where the maths is done and shown. So in order to calculate a figure, you can't do it directly on memory. You have to bring it in to a register where you can do some maths or shift operations or logical operations on them. So dedicated registers, you have the accumulator, which is like I said, like a calculator display on a standard calculator. The status register, so this holds flags. So if you've got a positive result or a negative result, some sort of error status, it's shown on the status register. The program counter holds the address of the next instruction to be fetched. PC. You've got the MAR, which is the memory address register, the memory buffer register, which holds the instruction from the memory address register and the associated data. So you have like a buffer and the main memory address register. Then you have the current instruction register, the CIR, which holds the instruction that is to be decoded and executed. So I've downloaded, I've brought up here peterhigginson.co.uk AQA assembly code has helpfully written an emulator to show how these programs run. And you can see here you've got the program counter, we've got 12 registers, we have the control unit, we have the current instruction register, the memory buffer register, the memory address register, we have the status code held there, the arithmetic and logic unit, which does the maths and shift operations, and we have some input and output. Okay, so let's go back to this. So we have the fetch, decode, execute cycle. So there might be a question on paper 2 that says, please describe the fetch, decode, execute cycle. So it's not a bad idea to try and memorize these steps here. Now, I'll just quickly go through them, how it goes. Okay, you've got the fetch part of the decode, fetch part of this little cycle here: fetch, decode, execute. Fetch the next instruction, decode the instruction, execute it. But you've got to describe what is done under each bit. So in the fetch part here, you've got the fetch, you've got the program counter points to the next instruction to be fetched from memory. So it's pointing to an address in memory where you have an instruction to be brought in. The contents of the next instruction is copied into the memory address register. the instruction of the memory address register is transferred via the data bus to the memory buffer register, and the contents of the memory buffer register are then copied to the current instruction register, and the program counter is updated to the next instruction. Then you've got the decode part, where it's just simply decoding the current instruction register, doing something with it to give a number to it. The decoded instruction is then executed. So whatever that instruction is, whether it's to add to a number to one of the registers, it will then do it at that particular point, and then this process is carried on and repeated. Now, what isn't on this slide is there may be a point after that execution, before you go into the next fetch, there may be an interrupt, which is sometimes brought in at this point. After the execution, we just check whether the printer's out of paper or something like that. So the printer will send, for example, if the printer runs out of paper, it will send a note to a input-output address to say, I want to do an interrupt, and before we move on to the next fetch instruction, the interrupt is then serviced. But that's it. Now, I got laughed at by some of my students for suggesting this, but you may want to think, what helped me when I did exams and I had a list to remember like this, is that I would think of a route that I would sometimes take, maybe out of college to home, and you think of certain points on that route where you can insert something. So here, PC, well, that could be a police constable pointing to an instruction to, come here, and then you've got that isn't the contents of the program counter. That is actually the contents of the instruction from the memory address is brought into the MAR. So you could have a PC then bringing that next instruction to Mars on the next point in your route. So if you think maybe leaving your house to go to the shops, you walk out the front gate, you've got your PC pointing to an instruction. Oops, let's go back. And then you've got the PC then dragging the instruction off to Mars at the end of your road, at a suitable point. You can then expand on that, think of your own journey, if you like, with these little mnemonics, these little memory tricks, and you should be able to remember that whole list. It may be something you may or may not want to do, but it probably is useful to do this. There may be a good chance that you may have to describe the fetch, execute, decode cycle, fetch, decode, execute cycle, and how interrupts fit into it. Okay, we'll move on. So the next thing that we need to talk about is addressing modes and how an instruction is held in memory. So the instruction is held in memory. You have the basic machine operation. So computers can't hold, add, subtract, or other commands. They can only hold noughts and ones. So you have this list of noughts and ones to represent the instruction. And we look at assembly language as a mnemonic, a memory aid, if you like, to what that instruction is. Okay, so this series of noughts and ones might equal add. You might have another number that represents subtract, and so on. The next bit that we need to talk about is the addressing mode. So the addressing mode is whether we access the address directly, or whether, so this number here is 1, 2, 4. This number here is 5 in binary. So if we're adding 5, if this is to add 5, are we saying that we're adding 5 or the number in location 5? So immediate addressing mode is actually 5. We're adding this number to the accumulator. If we say direct mode, so that number may be a 0 for direct mode, then we are directing to a location in memory to get the value that we're going to add. Okay, so we'll look at that in a minute. One question that you may get here is how many instructions can be called upon if we have 6 characters for the instruction. So the way to do that is, well, there's 2 ways. One is you're allowed your calculator in the exam, so you would do 2 to the power of 6, okay, which should be equal to 64. The other way to do it is just go 1, 2, 4, 8, 16, 32, and the next one will be 64. So this is an important point. If you're asked what the maximum value could be held in 6 bits, then that would be 63. But if we're asking how many instructions could be operated from, how many instructions could be held, or how many values can be held, well, it's 0 to 63, which is 64. Okay, that's an important point. Okay, so we'll move on. Okay, so this is basically addressing mode, so we can have an actual value, which is an address in memory, or the register where the data is held. So the addressing mode is typically 2 bits. There's only 2 addressing modes that you need to worry about for the exam, and that's direct and immediate. So immediate is the actual value, and direct is directing you to a location in memory. Okay, so we'll move on. Okay, so in this particular case, the addressing mode 00 signifies that the data value is 12 in this case, not an address. So that is immediate addressing mode. Okay, and then we have direct addressing mode with the 1. Okay, so we're directing to memory. So these are the instructions we need to worry about in the exam. There's just two lots of them. There's not that many. You are given them in the exam. So this one is to load the contents of this memory address into register 1, 2, 3, 4, whatever D is. So D could be 1, D could be 2, and so on. So we're loading that in. So the important thing is here is the instructions are all back to front except for this next one, okay? So we're storing that into that, or we're loading that into that, I should say. We're actually storing that into that. So that's the only one that goes the other way. If we're adding whatever is in the operand to that and putting the result in that. Now the operand can either be a value, okay, or it could be an address in memory, or it could be another register, okay. And we've got the subtract. We're subtracting that from that, putting the result in that. We're moving that into that. So I've seen a lot of students sort of mess this up where they've done it the wrong way round or whatever. It's that into that, that from that into that, okay. And you've got a comma between these, okay. So here's some example instructions then. The direct and immediate addressing in the mnemonic form, in the assembly language form, is we put a hash next to it. That means that it's actually 5 that we're adding to R2 and putting the result in R3, not memory location. And we signify that by the use of a hash. This instruction, we have memory address 300 is the operand. We're loading that in to there. and it actually is whatever's in the memory address. This is an example of code, okay? So we're loading in the contents of 100 into register 1. We're adding the value that is in 101 to register 1 and putting the result into register 1. So these two can both be the same, okay? We're copying the contents of R1 into R2. We're subtracting actual 5, okay, the value 5 from R2, putting the value in R3. And in this last case, we're storing, the one exception, we're storing the value in R3 into memory location 102. Okay, the other thing that we need to worry about is branching. So branching is done in 2 steps. Well, it is if we've got a condition. So if we're just branching to a label somewhere in the program, we'll look at that in a minute. If we're branching to a label, we don't have to worry about doing a compare first. But normally we would do compare these 2 values, and then we branch if equal to, or branch if not equal to, or branch if greater, or branch if less than. Okay. So this is an example. We're looping. This is not a brilliant example actually, because in the AQA assembly code that you begin in the exam, you'll never be asked to input. Well, I've not seen it. There might be, but usually you're told as an address in memory, move to another address in memory or whatever. So, but this is an example of inputting a series of numbers until the user inputs the value of 0. So if it's not 0, we jump back to the loop. The loop has a semicolon after it. Otherwise, we just carry on doing this, which is just simply adding the value that's been inputted into R1, putting the result in R1. Okay. And then at the end, we're moving the value of R1 into 100. So we're putting the output into memory location 100. Feel free to pause the video and follow that one through. Now, this is the last bunch of, well, second to last, I should say. We can perform logical AND or exclusive or a NOT operation. That's the only one that's a bit funny. Well, EOR is a bit funny. I would have expected that to be XOR, but it isn't. And this is logical NOT. So to give an example, this is an AND, okay? So we're doing an AND of those 2 values there. So the only one that would satisfy that condition is that last one where you've got 2 1s, 1 and 1 is a 1. Anything else is a 0. Now, that possibly could come up as an exam question, because this is what you would do with a subnet mask, okay? So you might want to check out subnet masking. I'm sure there's other videos that will do that. I may do one, I may not do one, but you might want to check that out. One question that you might be given is, write some assembly code to check to do a subnet mask. So you might be asked to do an AND. This is OR, okay, so you should be familiar with OR. 0 and 0 is 0, 1 and 0 is 1, 0 and 1 is 1, both 1s are also 1. Now the exclusive OR, or the EOR, in this particular case, is all the same as the OR, except if we've got both values all set to 1, then that is set to 0. Then finally the NOT, where we just do the opposite. 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0. Right, final 2 instructions. Logical shift operations. So we can move the bits that are in registers one way or another. Just slide them across. So if we want to slide the numbers to the left, Okay, logical shift left. So the value that is in R1 are shifted over to R2, one at a time. Okay, just shifted over like a little train, and we lose that end digit, and we also gain a 0 at the beginning. Okay, so that is the number that says we're shifting it left by 1, putting the result in R2. Likewise, we've got the logical shift right, where we are shifting what is in R1 2 spaces, or two bits to the right. So you can see that here. We've gained 2 zeros at the end, and we've lost those 2 zeros at the other end. Now, that concludes the instructions. Just going back to peterhigginson.net, actually, and a couple of exam questions. So I'm just going to look at exam question from a previous year here. Okay, it's the marking scheme. Like I said, you will get in your exam question the standard AQA assembly language set. So you don't have to memorize these instructions, you will be given them. Okay, so as I've said, there's no input in there, and you've got the OR instruction, the EOR, which is XOR operation, the the NOT instruction, perform a logical NOT operation. It looks like a move, doesn't it? But it isn't. That's, the move is this. Now, it also tells you here at the end, the interpretation, that a label is placed in the code by writing an identifier followed by a colon to refer to the label. The identifier of the label is placed after the branch instruction. Okay. The operand can be interpreted in 2 different ways depending on whether the first character is a hash or an R. So you can either, the operand in this particular case can either be a direct value like 25 is the decimal value of 25, or it can be a register. So that's quite important. It's not going to be, that's the operator, the operand, I should say. Okay. So the question here is, the Vernam cipher consists of a plain text character. By performing a logical operation between a character and the plain text part of the key. So there's 2 types of ciphers or encryption you need to worry about in the exam. One is the Caesar cipher, which you can look up, which is basically very basic cipher. So you could say that the key that you're going to use is +3. So if you've got the value of A, you want to make it a D. Okay, so you're moving 3 spaces forward, and a B will then become an E, a C will become an F, and so on until you get to X, which becomes an A. So it works around in a circle. But anyway, this question isn't about that. This is about the Vernam cipher. Now, the Vernam cipher is a perfect cipher, really. It's uncrackable, providing certain conditions are met. So the conditions of this are that you have a pad of letters which are totally randomly generated. So not by a computer, because computers aren't completely random. Some kind of, some kind of lava lamp or something that generates this code of letters. And that one-time pad needs to be larger than the message that's being sent. So a typical, the other thing is you actually give it by hand the one-time pad to the person. So typical example, a nuclear submarine is sent off into the waters of the of the oceans, and before it sets off, the Navy give them their set of one-time pads that are delivered to them by hand, and whatever they send by radio communication, even if another, the Russians or whoever is listening in, they'll not be able to crack it at all, because you would need that one-time pad, and that one-time pad is only on the submarine. There's only one copy of it. It's been completely randomly generated, so there's no chance at all of being able to crack it. The way that you execute this one-time pad, or make this one-time pad work, is by doing an XOR on it. So if you've got a plain text character held in the value in the memory location 101, you do an XOR of it, and you put the remaining key in 102, and then, providing the receiver has the one-time pad, they can then decrypt it using exactly the same one-time pad. So it sounds more complicated than it is. We're basically going to do an XOR. So I'm going to look at the Peter Higginson dot AQA assembly code, and I've already written the code in here. So I'm going to put a value. So let's put a value in there. So I know that 65 is capital A. Now 88 is the key for the one-time pad, and I know that that is an X. So we're going to say that the one-time pad is an X. So we're going to do an XOR of those two values, and we're going to put the result in memory location 103, as according to the instructions. So let's just assemble that, and then we will run it. And you can see the fetch, decode, execute cycle working in real time here now. So it's bringing the instruction in, the memory buffer register and the memory address register. And that has not worked because I have not put the values in, or whether I did put the values in, but they have been overwritten because I've assembled it and that has overwritten them. So let's do that again. We'll reset this, and I put my value of A and X in there. Okay, let's try that again. So the program counter is 1. Memory address register is pointing to the place that we're going to, 102. Now 103, we're bringing the instruction in to the memory buffer register and the current instruction register. And this time it's worked. So we've halted the program. So just to talk through this program, we've loaded into register 1 the value that is in memory location 101. We've then loaded into register 2 the value that was in 102. We've then done a exclusive OR those two registers, put the result in register 3, and we have then stored the value of register 3 in 103, which is 25, and then we've halted it just to be neat. Okay, so just to prove the point of the Vernam cipher, we're going to keep our one-time pad, which is X, and we're going to put the value 25 in there, and I'm going to clear that. And this time I'm going to reset it so that we get back to the beginning of the program. Yeah, those two values are there. I'm going to run this and we should get 65 back there, which is our A character. So I put the ciphered key in there and put in there. Obviously, this would work for a string of characters, and the one-time pad has to be at least as long as if not longer than the string of characters of the message. So let's run. This time we've gone to memory location 101. You can see in there instructions are being brought into memory. Values have been put in the registers here. And then finally, 65, which is the value A, is then being put to memory location 103. Okay, so that's the first example. Let's have a look at the next one. Question 2. So again, this is another year. These can vary in marks, and you certainly get marks for knowing about the processor and its operations, and then you might get some code to write. So again, every question we're given the value, we're given all the instructions. Okay, so this one here is write a program using AQA assembly language in the table above that will store the greater of these two numbers in R1. See, the registers R1 and R3 store a different positive number, and what you have to do is put the largest of these two numbers in R1. So basically just bring, if R3 is greater than R1, put that value in there, I think. Okay, so store 1 in R2 if the value originally in R1 is greater than the value in R3, storing 3 in R2 otherwise. So you're actually putting 1 in R2 if it's bigger and 3 in R2 otherwise. So it's important to read the question and just look what it wants. Now, I'm not going to write the code. I'm just going to go straight to the marking scheme. Okay, so one mark for each of these points, doing the comparison, doing the branch instruction, always terminating with the result, with the greater result in R1. So you know you've got 3 marks there straight away, and terminating a 1 stored in R2 when the greater number was in R1, and 3 stored in R2 otherwise. And there's some examples here. So you can see how the code works. You've got your labels. Do you know what? I'm going to copy it. I think example 3 is probably the way I would write it. So I'm just going to copy that into my assembly code here. Oops. Oh. And I'm going to assemble that. Submit it first and assemble. Okay, so you've got your code. We're moving the value of 1 into R2. We're comparing R1 with R3. We branch greater than if it is greater, if 3 is greater than 1. And that will go to done. Actually, I'm just going to check the set of instructions there on the compare. So compare the value stored in register with the value special in operand 2. So we're going to compare those two and branch if greater than to done. Okay, so if I think it's the other way around, it's R1 is the greater of the values, and then otherwise we are going to move 3 into R1 and then the value of 3 into R2. So it's a fairly simple program. Now what I'm going to do is I'm going to put two values in these registers and just see if we can, wonder if we can just override them. I've done this before. So R1, I'm going to put 10 in. Oh no, it looks like I can't. So what I'm going to do is I'm going to insert some more code. So I'm going to load into register 1, should be in capitals here, LDR R1, and I'm going to put hash 5. Now I'm going to make R1 bigger, and then LDR R3. I'm going to make that hash 5. So let's submit that. Okay. Bad parameter. It doesn't like my lowercase. Oh dear. Right, submit that. What does it not like? Doesn't like that I haven't got a comma. Submit. Okay. Okay, I've realised it actually wants a memory location here, not hash 10. So I'm going to use our favourite 101 and 102 for this. And in 101, I'm going to put the value 5. Let's submit that. 101, I'm going to put the value 10, I should say, and in 102, I'm going to put the value 5. Okay, so let's run that again. So it looks like, as per the instruction manual, actually, in the questions, if we go back to the questions, you can see here that it wants a memory location, not a direct value. Okay, with that LDR and the store register command. Okay, right, let's give that a whirl. Okay, so I've got my 10 in register 1, and we've got the 5 in register 3. I've put me 1 in register 2. I should have actually used the move command, shouldn't I? Well, to get the direct values, but anyway. Okay, so 1 is greater than 3. So we've branched to done, and it's finished. Let's just swap them around. So we'll put 5 in there and 10 in that one. So this time it won't branch if done, and it will do these two instructions here to swap these two memory locations around. So we need to reset to get that back to where it was. We've still got our values in 101 and 102, and run. Okay. And this time it's put the larger of the two values in R1, which is 10, and it's put a 3 in R2. So it didn't do that branch to done, but instead just carried on there to do those two move commands. And that's it. I wouldn't become overawed by these questions. If you see logical shifts or if you see XORs, just follow exactly what they want you to do and have a go at it. You may get some of the marks just by putting the instructions in, but do remember that the instructions work back to front. Okay, with the LDRs, you've got to be going to memory locations. It's only the move where you're allowed to move two registers between the two, or do this direct number into a register. Okay, that's it. All the best for your exam on Wednesday.